How does inductor current ripple affect DC-DC converter design? Imagine trying to keep a steady flow of water through a pipe when the tap keeps flickering on and off. That flickering is like the current ripple in a DC-DC converter. It might seem small, but it has a big impact on how these power systems are built and work. When designing a DC-DC converter, understanding how the inductor current ripple influences performance is key. The inductor in a converter stores energy when the switch is on and releases it when off. This switching creates a ripple, which is a variation in the current superimposed on the average current. The size of this ripple depends on factors like the inductor's value, the switching frequency, input and output voltages, and the load. A larger ripple means more variation in current, while a smaller ripple means the current stays more steady. Designers usually aim for a ripple around 20 to 40% of the average inductor current. For example, if the average current is 10 amps, a ripple of about 2 to 4 amps is typical. This range helps keep the converter in continuous conduction mode, where the inductor current never drops to zero. Operating in this mode makes the control of the converter more stable and reduces output voltage fluctuations. If the ripple gets too high, above about 40%, the converter might switch into discontinuous conduction mode at light loads. In this mode, the inductor current drops to zero during part of the cycle. This can cause issues like less stable output voltage and increased electromagnetic interference. It also raises peak currents, which can lead to higher conduction losses and more heat. These higher peak currents mean the inductor and other components need to handle more stress, increasing size and cost. On the flip side, if the ripple is very low, below 10%, the inductor needs to be larger. Bigger inductors are heavier and more expensive but help keep the current steady even at low loads. This makes the output voltage more stable and simplifies the control circuitry. However, the trade-off is that the converter becomes bulkier and more costly because of the larger inductor. Ripple current also affects the output capacitor. Since the inductor charges and discharges during each cycle, the ripple current causes the output voltage to fluctuate. To keep voltage ripple within limits, designers often need larger or higher quality capacitors if the ripple current is high. This adds to the size and cost of the overall power system. In the end, the ripple current influences many parts of the converter design. It determines whether the converter stays in continuous conduction mode or switches to discontinuous mode. It affects the size and cost of the inductor and output capacitor. It also impacts efficiency because higher peak currents lead to more conduction losses. Designers balance these factors by choosing a ripple current around 30% of the average current. This sweet spot helps optimize size, efficiency, electromagnetic compatibility, and output voltage stability. Whether working on renewable energy systems or power management circuits, understanding and managing inductor current ripple is essential for creating reliable and efficient DC-DC converters.